Daniel, it's great to have you here. You just came in from Cambridge. You're coming for the Scale Up workshop tomorrow as well. You have a little talk section there, and it's great to have you. Thanks for coming by.
Thank you so much for the invitation.
Yeah, so we have a few minutes here together now to talk a little bit about your work. And you just told me you used to be on TikTok. What's that all about?
Yeah, it's a funny story actually. So maybe a quick introduction on myself. So I did my undergrad in chemical engineering at Imperial and then went on to do a PhD at Cambridge in AI for chemistry. And there my work was really focused on how to apply AI strategies, machine learning to process development, to understanding chemical reactions, and obviously Bayesian optimization was a big focus here. And to your question, during COVID, I, like so many other people, were trying lots of different things, and I figured that the world could need some more chemistry education. So I started making videos about chemistry, math, physics on TikTok and started posting them. And yeah, the first 6 months I got like 100 views, but then all of a sudden people started liking my content. I got better at making these videos, and then I ended up getting picked up by Chegg. That's a big tutoring company, to make videos for them, which was so much fun and great supplemental income alongside my PhD. And I actually continued making these videos after finishing my PhD, and it ended up being the income from TikTok that actually enabled me to start a company, not have to rely on income from a job. I could pay my rent using this money from TikTok. So it ended up being like a fun, side project, something I would do for fun, just to teach people about chemistry and how much fun it is to mix, vinegar and baking soda.
Yeah, that's
in
cool.
your own kitchen, and then that turned into kind of the enablement for me to start ReactWise, because I could pay my rent using this money I was making on TikTok, while also making videos that would make people smarter. And
well, that's a great story. So those videos are still out there, so people can watch those.
Yeah, absolutely.
Wonderful. So I mean, straight into it, then of course, ReactWise is your company. I see you're wearing your swag right now. What's ReactWise about, and what are you guys doing?
Yeah, thanks for asking. So ReactWise is an AI copilot for process optimization. We're essentially an optimization platform for the pharmaceutical industry. So that means chemists that work in pharma can use our software to essentially find the ideal process recipe for novel drugs. To maybe put this into context of what exactly does this mean, imagine that you are developing a recipe for a novel drug. You need to find out which chemicals am I mixing together, at which time, which additives might I need to have in my mixture. And our software platform helps the chemist by suggesting how to best design this recipe. And right now there's a lot of trial and error involved, and with our software platform we can save time in pharma by over 50%.
That's quite impressive. And you guys have been working on it since 20...
Yeah, so we actually started researching, my co-founder and I, Alexander, we started research into Bayesian optimization in our PhDs.
I see.
So I first published on Bayesian optimization, was it 2020 or 2021? I can't remember now. But basically in a machine learning for chemistry side conference, or side workshop to NeurIPS, where together with my colleague from my research group, Kobe, we worked on a transfer learning strategy for Bayesian optimization. And that was kind of where my first interest in process optimization started. So that's, like 5 years ago now.
Yeah.
And then kind of throughout the rest of my PhD, I was interested in everything from, computational chemistry, data engineering, and then kept this interest as well in Bayesian optimization, and continued to work on that, and ended up publishing a paper in ACS Central Science.
Mm-hmm.
And it was these ideas that led to ReactWise, essentially. So Alexander and I had been working together throughout our PhDs, and then towards the end of our PhD, we were talking about the possibility of starting a company together, and how there's a big problem in pharma right now that process optimization can be really tedious, and most chemists are not going to learn how to code. So how can we build some software platform that will make it really easy for them to access the algorithms that we developed in our PhDs.
That's great. So you really were kind of kickstarted by both your PhD, meeting the right people, and then making videos and TikToks. It's a great story.
You could say that.
Yeah. So making software and particularly these algorithms available in the most simple way. That's something I just talked about with Morten as well. What's kind of like the biggest challenge you find in trying to make it simple? You know, like they're already challenging, but making them simple is a challenge in itself. So like, what's the struggle there?
Yeah, I think that's such an excellent question. And if you find the answer, please let me know. I think there's this fundamental challenge in building an easy to use software platform that by the nature of making it simple, there's just some things you cannot do. And if you let the user define everything, the only way they can do that is by writing the code that literally specifies the math behind what you're doing. So at the end of the day, you're just never going to be able to give the user every single like knob to tune. So I think it's really the job of the founders, me and Alexander, to draw that line of have opinionated software that makes it possible to optimize chemistry without having to write code, and understanding the user and the process well enough to know where to draw that line, coupled with, of course, having an amazing team with great intuition on UI and UX and understanding, even something as simple of like, where should the buttons be? If it's intuitive and that like permeates the entire software platform, it just becomes such a pleasure to use. And it's one thing that we're surprisingly already seeing now. Big legacy softwares obviously have had decades to develop their software, so they have infinitely many features, which can often be overwhelming. We're only 2 years old, but already now we're seeing, as we are adding features, this just creates a tree of possibilities, and we need to make sure that we still keep this like essence of being easy to use.
So being easy to use is really a unique selling point you would put out there?
I would definitely say so, yeah.
That's great. Cool. So obviously we're having the scale up workshop tomorrow. So we're putting that scale up workshop together not just because we're interested, so that's Alfred and I, not interested in good experimentation, but also for bottleneck situations, and scale up is definitely one of the big ones there.
Yeah.
You mentioned just before you've done some work in Kinetics.
Yeah.
And I think you said you also have a new feature on the platform being released or coming out. How does that work? I'm a statistician. My chemistry knowledge is limited, and I'm sure that the people listening are also interested to learn a little bit more. But what's Kinetics and why is that relevant?
Yeah, amazing. Thanks for asking. So maybe to take a step back, our goal at ReactWise is to connect every single part of process optimization and have everything within our software platform. So that's tying together the super early stage exploration in terms of synthesis. So when you're doing high throughput experimentation, designing well plates, through to when you're identifying your categorical parameters. So, figuring out which solvents, ligands, bases, and so on with our Bayesian optimization tool, and then taking that through to all the way right before scale up readiness, or right before scale up, getting ready for scale up. And one of the big challenges and questions here is understanding how your process behaves. And the best way to understand how your process behaves is kinetics, because what you're essentially doing is very simple very simple actually to explain. You're making measurements of each component, the concentration as a function of time. So you're measuring for your reactant, how does that decrease as a function of time? For your product, how does that increase as a function of time? And then essentially all you're doing is with that data, with that time series data, you fit ODEs to it.
The ODEs are?
Ordinary differential equations.
And those ODEs help in...
Yeah, so the idea is once you can fit, so essentially I can also just say model, it happens to be an ordinary differential equation, but I can just say model. You fit models to this time series data, and the point of that is you can now understand how will my system behave under different initial conditions.
I see.
So let's say I double the amount of starting material, how will that impact my final product?
Yeah.
and you can start asking questions like, if I introduce this impurity, or if there is this impurity, like how will that impact the product? Or let's say it's a hot day in the production facility and the temperature is 5 degrees higher. Will that have a big impact on my product or a small impact?
Yeah.
So if you have this model that describes your system, you can understand your system much better. And really the core to unlocking this is time series data.
Okay.
Because oftentimes in the intermediate stages of process development, you're running round bottom flask reactions. You're running a reaction. You're only measuring your basically your outcome. So you have no idea how you got from A to B. You just know A and B.
Yeah.
But with time series data, you can fit these models that allows you to extrapolate. And ultimately, that's what you need for scale up.
Exactly. I was going to say, I mean, extrapolation and understanding your system on a small scale is, if not the most important thing before you move on to run it, producing at a bigger scale.
Yeah.
That sounds great. So obviously you at the interface of chemistry and machine learning and AI, as we might say. That gives you quite a powerful place there because you understand the language of chemistry, but you also have the experience of making machine learning work in that place. You have a co-founder.
Yes.
How is he also a chemist, machine learning person?
Yeah, so I think it's actually great. So Alexander and I are both at the intersection of chemistry and machine learning. So we both have a hybrid skill set, but I think very few chemists or no chemist would call me a chemist.
Yeah.
Because I've actually, I've not done small organic molecule reactions in the lab. My work was purely computational and computational chemistry and machine learning. While Alexander does have this wet lab experience. So we came from different places, me from the computational background and him from like the wet lab background. And then in our PhD, we basically like got closer to each other by working on hybrid methods. And I think to an outside observer, it looks like we have the same background because, it's both AI for chemistry and you're both are doing hybrid.
Yep.
But obviously hybrid is a spectrum and he has, much stronger wet lab chemistry skills and understands, how people would work in a lab because he was in a lab himself, while my background is stronger on the computational side. So I think we make a perfect co-founder pair because on one hand we're very similar, but on the other hand we're actually very different.
Yeah, so it's always important to be complementary, whether it's marriage or marriage in business. And I think you guys have great footage out there. I think you have your own lab space in Cambridge as well. So you're running and collecting data.
Yes.
What's that data for? I suspect maybe some transfer learning or something like that. So what's the role here?
Yeah, absolutely. So we're very fortunate to be supported by Innovate UK, and they granted us they granted us funding for the development of an algorithm called Zero Shot API. API short for active pharmaceutical ingredient. And the idea with Zero Shot is that you can predict what the ideal conditions would be to synthesize a novel API without having to do any iteration in the lab.
Wow. So
the underlying premise of why we're doing all these experiments is, can we build data sets? Can we basically generate data sets to build models that can predict chemistry? And we're starting with the most well-known and most often used chemical reaction types, chemical reaction classes. So Suzuki couplings, Buchwald-Hartwig couplings, amide couplings, and training foundation models for each of these reaction classes. And then the idea is that one of our clients can then plug into our data sets and say, I'm doing a Buchwald-Hartwig coupling myself. The structure is going to look like this, and I'm interested in these conditions. And then we'll do pre-training on our data sets and suggest you should do this experiment, and you'll get a good yield for the chemical reaction you want to do.
That's quite impressive. Well, I have so many questions, but of course time is limited. So I remember we last met, we met in Cambridge also, but we also met at the Automated Synthesis Forum, right? That was in London before Christmas, I think.
Yeah.
By the way, great conference, right? I mean,
I love that conference.
30 years or something. And I highly recommend anyone to go. Is it free to attend? I'm not sure. I think you have to get a ticket, but you guys were exhibiting anyway, so you were part of supporting the conference because it's is supported by the people exhibiting. So automated synthesis obviously means automated synthesis. Of course, it's interesting that that's been running for so many years. But right now, of course, the year 2025 was the year where we had more than $2 billion investment in automated science, AI for science. Of course, people are throwing it all into it together. But of course, AI is data hungry. So who's going to produce all that data? I guess you guys have maybe some kind of level of automation in your lab. But what I'm trying to get to is like, what's your perspective on automation in a laboratory and automation in chemistry? So can it be overdone? Is it currently undervalued? What's the future of that? And what's kind of like your most surprising learning so far?
Yeah, excellent question. And I think it can really be tackled from many different angles, because there'll certainly be areas that are over automated, and other areas that are under automated. So maybe if I start by thinking about or talking about what we do in our lab, we're running high throughput experimentation, running 384 well plates to generate our data. And this is really a mixture of lots of automation, but also manual steps. So maybe we start by the preparation of stock solutions. Like really, I think one thing about automation is you really need to get into the nitty gritty, because if you just talk about, automation at a high level, all the interesting bits get lost. So in terms of our workflow and preparing stock solutions before you can even get started, that is a step that's still being done yet manually, but you just need to create one stock solution per component. But then the dosing into our well plates, we're using automated hardware. So we have an open trans in our lab that we've programmed to basically with a multi-channel pipette that will automatically dose our entire plate for us. And that obviously means that if it was a human that had to dose everything, it would take absolutely ages. But now it means you can actually just press play after having written the program and come back like an hour later and it's all done for you. Which is what allows us to screen thousands and thousands of reactions over the course of a few weeks. So I think in terms of data generation, this is one of the most obvious use cases where you can have a massive impact with automation, and that's already possible today. So I think in terms of like the batch chemistry and the high throughput, like it's absolutely critical, because you just cannot get good throughput without automating at least parts of it. Then on the other side, if we look at flow chemistry, for example, we also really like flow chemistry. We're going to Flow Chemistry Europe later this year. We went last year as well. And actually the ACS Central Science paper I mentioned previously, where we were validating our transfer learning algorithms, that validation was done in flow. And flow chemistry, I think, is also an area that really lends itself to automation and closed loop optimization. But here, I think the big challenge is that you can only do certain chemistries, first of all in closed loop and second of all in flow. So I think it's also just a question of how big a percentage of pharma chemistry can actually be done in a closed loop. Like sure, we could solve it, but or let's imagine hypothetically that we solved closed loop optimization, whatever that means. But if it's only applicable to 5% of the reactions that are done in pharma, how big of an impact is that going to have on the industry as a whole?
I mean, it's such a crucial and interesting question. I know that Sanofi was presenting their new automated lab at ASF, where they kind of teased it. But the crux of it all was that on the last slide, they were like, we can do about 90% of chemistry. But the other 10%, it might explode, and that's why we don't do it. And of course...
I would actually think the chemistry that explodes is exactly what you want automated, because you don't want humans next to it.
That was a very interesting point. No, I agree, and I think convenience and doing what we've done so far is convenient, right? And it's maybe like when we go all the way to the budgeting decision, it's easiest to budget for, right? We know how much it costs, we go for it. But of course, how are you going to budget for, automating the dangerous chemistry if there's no precedent for it? That's a whole question mark. I mean, Sanofi gave a great talk because they also showed that they've dipped their toes into automation like 5 times in 3 decades. So 2025 is a great year. Lots of money going into that. And obviously we're going to see in the next 1, 2, 3 years how these things all interface. Why did you guys choose an OpenTrons?
I think OpenTrons is great. It's very cheap.
Right.
Everything is open source. I'm a big fan of open source software and hardware. Yeah, and it works.
Yeah, it's great. Yeah, we were running experiments with a Beckman i7 that's obviously in biology right now. But it always blows my mind when you do that calculation. You have like 8,500 steps, and you're like, I just wouldn't want to do this with my own hands. So yeah, automation plays a role. I think it definitely can be overdone. You highlighted that as well. But yeah, I mean, coming maybe to closed loop, you kind of talked already now. So what does closed loop mean for you and maybe for ReactWise?
Yeah, so I think the best example is the closed loop that we've ran previously. So we both were working with VaporTech during our PhD, closing the loop in flow chemistry, doing CH activation reactions, and essentially mimicking this Bayesian optimization cycle where there's a brain that's designing the experiments, which in our case is obviously our software platform, that can also write the machine instructions for which chemicals to mix together in what ratio, sending that instruction to in this case a VaporTech platform to actually run the experiments, sending off the result to some kind of analytical equipment that can give you a yield percentage or a signal, and then feeding it back into our software platform to analyze that result and convert it to insights. So what does this mean? What's the next experiment we should do? Where we're very much focused at ReactWise on being the orchestrator. So developing the best algorithm to learn from this data to suggest the next experiment.
Yeah.
So in terms of what the user can do in our software platform, we're very focused on, in our software platform, keeping things simple and making sure that it's a software platform that everyone in the entire team uses, as opposed to some other softwares. We see there's a tendency to the development of a power user that everyone goes and asks this person.
Which doesn't scale. Right?
Exactly, which is the opposite of what we want. We want a software that everyone uses. Yeah. More similar to an ELN that's built for the whole team. Having said that, we also have a fully spec'd out API that our customers can request access to, and we're working with various different customers right now actually requesting, and they've been granted access to our API so they can run this automation. Though obviously when we're working at the API level, then it gets a bit more technical again.
Yeah.
But it's just very important to note that we have both sides of this coin.
Yeah. For sure. I mean, I think the answer is somewhere in the middle. Some people will be heavy API users. API means application programming interface.
Different API.
Different API than the active ingredient. But I think it's going to be a mix. I think it's not a normal distribution of how people will use these tools. I think there's going to be kind of the power users who will definitely have to link into an API. But I think the trick is probably kind of to support the best subgroup in the best way. And you mentioned that before already. You have to make a trade-off between how many hundreds of buttons you provide or making it just really simple. So looking a little bit then into the future, so tomorrow the scale-up workshop, chemistry and biology and other materials, whoever needs to scale up something for production. And then we've got, of course, the current AI buzzword and the benefits that we hope to get from that. What do you see as the biggest bottleneck in that whole kind of equation of we're going to use AI and apply to all kinds of sciences? What's the biggest bottleneck? Just to list some, is it data? Is it humans? Is it politics? Is it lack of money? What does ReactWise see the biggest danger, I guess?
Excellent question, and I'm not going to cop out by saying all of above.
Yeah.
Yeah, I think it's again hard to say because it depends so much on the specifics. Um, I think there's a few very large and significant bottlenecks. The first bottleneck on the data side, the ability to train these foundation models and have a kind of a ChatGPT moment in chemistry where all of a sudden you can do zero shot prediction of any chemical reaction.
Mm.
I think that would be a real game changer. Um, the idea that you upload a product molecule and you can have a closed workflow that's doing the retrosynthesis, doing the condition prediction, then doing a forward pass to verify the result, um, and having confidence that the conditions predicted are reasonable, and then feeding that directly to automated hardware and analytics to carry out the experiment. Like that's the dream. And then, couple that and do multi-step synthesis, all of a sudden you can manufacture an entire API or 10-step synthesis without any human involvement.
Yeah.
That's this idea of dial a molecule that I think was this first formulated as a grand challenge like 25 years ago or something.
Okay. Yeah.
So it's been something that the whole industry has been working towards for many, many years. And I think every year we get one step closer. But I think one fundamental challenge is attacking the problem of prediction from like the data and the machine learning side. We just don't have good enough low noise data sets. First of all, they're open source. And second, I think just in general, chemistry is a noisy science. Like the data generated is just hard to build models on. And couple that with the fact that when you're doing something at even a medium-sized scale, you have a lot of confounding variables, or you're not just going to have a pure 2-component system or 3-component system. There's going to be lots of impurities or additions or unexpected things happening in your reaction vessel. So I think it'll probably, I don't want to say impossible, but I can't imagine that in the near future we're going to have like this general purpose can predict anything model in chemistry. What I believe, and I guess what as an extension what we believe at ReactWise, is the approach of doing a reaction class specific approach and really building the building blocks. So we can't predict any of the 10 to the 60 molecules how to manufacture them, but if you're doing a Suzuki coupling within this region of chemical space with these types of substrates, then we can give you very good predictions.
Yeah.
That's how we would tackle it from the data side. That's what I believe is much more doable today. And then I guess if you tackle it from the other approach, from the simulation side, there's lots of simulation happening in drug discovery and docking simulations and so on. MD simulations when you go to slightly larger systems, but I don't see anytime soon being able to simulate how to do reactions at scale. Just because as I was alluding to before, when you're scaling something up, it's a slurry. You've got a multi-component system that's very, very complex with a mixture of heat and mass transfer limitations and kinetic limitations. I just don't seeing the simulation side being a solution to that. So the reality is probably that there will always be an element of trial and error required. So what we're trying to do as ReactWise is to eliminate as much as possible of that trial and error, but still having the ground truth be what you see in the lab.
I fully agree. I mean, that's a conclusion I've come to as well over the last few years. You can do a bit of simulation, you can have these things, but you will come down to trial and error at the end of the day. Like there's nothing more harsh than the feedback you'll get from nature that it just didn't meet your expectations, and that is kind of the game of science anyway, isn't it? So we can either be sad about that or we can just happily engage with it and, as you say, try to reduce as much variability as we have.
Yeah, it's interesting that we come up with better and better strategies for guessing really, really well.
Yes, yeah. There's a fine line between gambling and guesstimating.
Exactly.
But one is literally just gambling, and the other one is somewhat more informed, and will on average get you to the better result eventually.
Yeah, yeah.
Okay, so tomorrow we have the workshop. We're gonna have a DOE component in the morning. Of course, DOE is let's say a second generation design of experiments from Bayesian optimization is a little bit more, let's say, sophisticated, more model machine learning kind of thing. And then in the afternoon, we're going to have lightning talks. One of your talks is going to be that. What are you looking forward to in the workshop? I don't know if you had a chance to look at the agenda, but is there anything that strikes you?
Yeah, I'm actually really looking forward to the DOE workshop. I'm obviously familiar with like the math and the methodology behind DOE, but less so what that looks like in terms of implementation in the lab. Because like I said, my background is purely computational, so I think what I'm looking forward to the most is getting some, I guess, a bit more hands-on experience with what might a chemist be using DOE for.
Yeah.
On a more day-to-day application focused way, rather than what I've been looking at in terms of DOE so far is looking at data sets and how to build models given DOE math and multi-term equations. I think that, I guess, bringing it down from like the math that I'm comfortable with to like, okay, but how is it used day to day? Because I think Bayesian optimization and DOE, while they are complementary and a lot of people use DOE for all these types of problems, I think they can serve different purposes.
Yeah.
And I think there's different challenges where either DOE is better suited or BO is better suited.
Yeah.
So as with most things, I don't think one is going to get rid of the other. I think the best state is a mixture of both.
Yeah, I agree. Yeah, it's about the tools and when to use when tool is not. There's no silver bullet for this.
Yeah.
Great. So as a final question, is there anything that you would like to ask me?
Yeah, I would love to hear a bit more about your thoughts on how we can learn about scale-up challenges across the sciences and across disciplines.
Yeah.
One thing that still, I don't know if confuses me is the right word, but looking at automation in chemistry and automation in biology, I see very big differences. And like I think you're referring to like a peptide synthesis, like 8,000 steps before. How is that possible in biology, and why is a 10-step synthesis in chemistry like an impossible problem requiring a PhD, while you can do 8,000 steps in a row in biology? And what learnings do you think we can have between the sciences?
Yeah, so the 8,000 steps was more like that's how many liquid handling steps you have to make. I see. But regardless, it's definitely true, the characterization that biology is very different to chemistry. I think it is just intellectually interesting to ask the question of why do we have liquid handling? And I think a lot of people are confused because they see those liquid handling machines which have been around for decades, literally decades. And they're like, well, does this mean automation has been solved? And the answer is no, because not everything's a liquid, first of all. So there's a lot of things that require powder handling. Andy Cooper in Liverpool, I don't know if you know him, with the materials factory. There's a whole bunch of research that's happening right now about how to handle powders, because not everything's a liquid. But then also in biology, you have just very different constraints. You have these kind of stock solutions, and you have the cells which are literally kind of alive. And at times, scientists talk about cells as if they were, the kind of persona anyway. So like human cells are apparently much more, finicky than like some robust yeast cells or something like that. I'm not a biologist, but because of that difference, that's why we see, and that's why we will need different automation equipment. And that's where it gets hard, right? Because it's not like I can order any kind of robot from China or factory, right? These supply chains, everything has to be built up over years and decades. And what we see kind of right now is that companies like Opentrons, I asked you about why did you choose Opentrons? They exist because of that, partially, right? Because they want to bring more flexibility at a more affordable price. I think price is, as always, what determines innovation and the right innovation. And so right now, a lot of sciences are struggling to afford proper automation. And then on top of that, we have, of course, market factors, because why do we have liquid handling so well developed? It's because diagnostics, like healthcare spend is an amazing, huge amount of GDPs. Everyone needs to get, a lab test result done in less than 24 hours. I mean, the lab automation people, the whole vendors had absolute insane demand during the pandemic, right? Because everyone needed those COVID tests. And then, of course, it crashed after that as well. But that's where the confusion is, right? Because lab automation for diagnostics is not lab automation for kind of like closed loop, kind of like scientific research, which is what we are talking about.
I guess diagnostics is also a solved problem that you're repeating, while science is something unknown that you're trying to do for the first time.
Yeah. And so I think a lot of confusion comes from simply the same term used for very different problem sets. And yes, I think chemistry is definitely ahead. And flow chemistry is really interesting.
You think chemistry is ahead of biology in terms of automation?
Well,
I was going to think that biology was ahead of chemistry, but
it's maybe my perception. Maybe it just tells you who I talk to. But like when when I look at the biology experiments, the data that I have to look at, and all the things that go wrong there, I'm always like rather discouraged, about the quality of data that even that.
It's funny because I mostly look at chemistry data, and I was thinking that biology was much better optimized.
Maybe both as well. Yeah.
Maybe the grass is just greener
on the other side. Honestly, it could be that case. I mean, the one chemistry thing that I worked on was actually not automated at all, and I think the fallacy there is that somehow you trust the human precision more, but it probably was quite noisy as well at the end of the day. I mean, we had replicates. Obviously, the best way to check whether you have good data is run the same thing again and see if you get the same result. But I think it probably maybe depends on the application. I mean, biology itself, of course, has a huge range again. So some experiments are just much more robust and repeatable than other ones. And I guess maybe that's the same in chemistry as well. So some multi-step things are probably much easier to mess up than a more simple baking soda, I guess. But from my experience, I feel like just the fundamental paradigm of liquid handling, that's pretty solid. I think that's good. That is what people are building on. I mean, we have those boxes, and then the plate comes out, and we've got a whole suppliers that provide that. I mean, Sanofi again had shown a whole kind of cart system. It's interesting how much time they spend presenting just how they can move around carts. It's like these are the real problems, right? It's not the science, it's not the reactions, it's not the data management. It's like I have a cart in a lab, it's moving around. How do I scan it? So I think these questions, and that's I think what you said as well. Like it's the details that matter here, and they really do. And I think that's also kind of like where the 2 billion from 2025 is kind of like really underestimating how hard that whole lab automation thing is going to be. But yeah, honestly, maybe I need to check my priors again. Maybe chemistry and biology can be both easy and hard to automate, depending on what you're looking at. But yeah, I don't know if that answers your question. I kind of sidetracked there.
Yeah, I think it's super interesting to see your thoughts. I guess if you've been looking more at biology data, you have much more insight than I do on the intricacies there.
I mean, that's just one thing. I mean, another one was there was also an alloy project. That data was pretty crazy. And then what else? I mean, it's also like human data. I've also looked at kind of like human, behavior to ads on emails and stuff like that. It's also really interesting because it's also not noisy as you think. So yeah, noise is something we talked about with Morten as well. It's definitely something he will talk about tomorrow as well. Yeah, so I think what we're going to see is a shift in the next years through automation, through machine learning, more statistical thinking. But no one knows what it's going to look like in 5 years.
I think a big change as well. One thing is the algorithm and the possibility and capability. Another thing is people's mindsets. And once the first person in a company has seen that, oh, I can actually save 5 minutes or 5 hours or 5 days, depending on the task, robustly and reliably, and then tells one colleague about it, who tells four, and then all of a sudden, like, I think that'll be accelerating over the next many years.
Yes.
And one thing I've reflected quite a bit on, Bayesian optimization obviously has existed for a very long time. I think ChatGPT and the release of ChatGPT was probably one of the things that kickstarted the appreciation of what AI can do, even when using non-LLM methods. And I think LLMs probably did more for BO than BO did for BO.
I have nothing to add. I fully agree. I think it's kind of some reverse mechanism going on here. And it's true. I mean, there's a paper Andy Cooper just put it out with, I think, Abdul Latif from Liverpool, where they used and compared BO and LLM, and their conclusion was, I haven't read the paper yet, that it's LLM plus BO that gets the best results. But yes, I mean, I think we both know that LLMs is a tiny part of the whole set of models that exist in machine learning. Of course, ChatGPT is what we call it, the same way we call something Googling when it's just page index. But yes, so everyone in the grammar knows about AI now. And
everyone thinks that LLM and AI is just like the same, synonyms of each other.
Yeah, which I guess for the time being they are in the vast majority of people's consciousness. But the reality is, of course, that with Bayesian optimization you have a much more principled approach. But we will see what comes out of it.
What's your take on foundation model development and using data to build models, either fine-tuning LLMs or transfer learning based optimization, or even neural networks, XGBoost, different types of models?
My take is that I haven't concluded. I haven't made up my mind yet. I think it's really interesting what TAB PFN. I don't know if you heard of that model, but tabular prior-fitted networks. The paradigm is so radically different to fundamental statistical education, or even classical machine learning. I mean, calling machine learning classic is already funny, but that is the next shift we're in. My statement is very simple. Let's do some science. Let's compare methods. Let's do good benchmarks. I think chronically, new areas come up with very bad and biased benchmarks, and so that's why it's very easy to temporarily look like you have found something really great, but then overall it's not that great. And so I think the fact though is that TAB PFN and these kind of models are doing exceptionally well in a lot of benchmarks, and we are yet to determine that. I think many people have already concluded it's great. I'm not there yet, but I'm taking my time, I guess.
Yeah, super interesting.
Yeah, cool. Well, thanks so much for your time today. I'm looking forward to your talk tomorrow.
Thank you so much for having me.
Yeah,
it's
wonderful.
very fun.
Thanks, Daniel.
Thank you.